Okay, so far we have focused broadly on intraseasonal timescales where we looked at both mesos and MJOs, but I decided to add a few podcasts from this nice paper by a group of MJO scientists who have looked at 50 years of MJO research and progress. There have been many review articles along the way. This one focuses mostly on the period after the last review, which occurred in 2013 or something. Okay, I will show which paper that is in a minute. But to orient ourselves a little bit, we have been looking at various MJO structure figures, starting with the canonical one that Madden and Julian had originally drawn in 1970s, 71, 72, when they initially discovered this mode. And that was a schematic, but now with data we are getting better and better depiction of MJO structure, propagation, 3D structure, and so on. Okay, and still many science questions remain, so we will look at those as we go along by starting with this podcast, which states the key feedbacks that we are interested in. Okay, so here is eastward movement of the MJOs. There is the convective phase over the Indian Ocean. We have seen this in many other ways, as I said. Very strong upward motion in the center of the convective phase of MJO. Surface convergence. We talked about various theories about frictional convergence instabilities, convective moisture feedbacks, cloud radiative feedbacks, and convective large-scale circulation feedbacks. All are key components. You have a divergence at the upper level, and then you have subsidence ahead. This is of course at the intraseasonal time scale. This is not the Walker cell, Hadley cell that we usually talk about, right? So ahead of it you have the downward motion, sunny, dry conditions that organize the SSTs to be warmer. But what are the details that actually make the MJO propagate eastward? You need specific kind of heating, moisture loading, instabilities, and waves to drive the eastward propagation. So we will look at that as we go forward. In this particular series of podcasts on intraseasonal timescales, we didn't focus so much on the index, so-called real-time multivariate MJO mode index, RMM, that Wheeler and Hendon came up with. But this is how it typically is depicted. It takes OLR, winds at 850 hectopascal, 250 hectopascal, does combined EOFs, finds the first two EOFs with PC1 and PC2, and then there are RMM1 and RMM2 indices created out of that to track the progression of the MJO. And this is typically a counterclockwise movement going in different phases. So you can see here you are showing the phases. So phase 2 and 3 here, phase 4 here. So phase 1 and 8 are shown here. So that's in the Western Hemisphere and Africa. So you can track a particular event. For example, here you're starting at 5 days, 10 days, 15 days, 20, 25. So you have this counterclockwise movement. And the general idea is that when the phase transitions are outside this inner circle with unit 1, then the MJO is strong, the signal to noise is high, it's very easily tracked. But when it is inside here, then it's rather weak. And I will just leave it there. You just have to remember that phase 1 is still in the Western Hemisphere, so over the Atlantic. Phase 2 and 3 come into the Indian Ocean. Phase 4 and 5 over the maritime continent. Phase 6 and 7 over the Western Pacific. And then the sea surface temperatures get colder, so there is not much convection happening once you get past about the dateline over the East Pacific cold tongue, and then some signatures transition across the South American continent into the Atlantic and come back over the Indian Ocean. We had mentioned primary and secondary MJOs. Secondary MJOs are the ones that have been reignited from the previous MJO and so on. So if it goes around and gets re-energized over the Western Indian Ocean, then it becomes a secondary MJO. But if there is some trigger, let's say from the extratropics, that generates a new MJO, then that's a primary MJO. Okay, so this is the paper, 50 years of research on the Mann-Julian oscillation, recent progress, challenges, and perspectives. I will record a few podcasts on this. Xianan Jiang is leading it, but there are all the other big names: Adams, Kim, Maloney, Chidong Zhang, Charlotte DeMott, and Klingman, and so on. This is from TRIM data, Tropical Rainfall Measuring Mission data, which made it possible to create such beautiful maps compared to the schematic that Mann and Julian had done, for example. This is filtered time series of rainfall, I think, but yeah, so you can see the convective phase, the dry phase, so the negatives here. So here is phase 1 in the Indian Ocean. Phase 2 is more towards the east. There is a transition across the maritime continent during phase 3, 4, and 5 here, and you can see some signatures here. Many of the MJOs actually get detoured. There is lots of literature on what happens to MJOs as they propagate across the maritime continent. Some of them seem to get stuck over the Indian side, some of them weaken and reappear here, some of them get detoured into the region here between Indonesia and Australia, which you can see clearly as a signature here, and those that get detoured also tend to affect the South Pacific convergence zone greatly, with cross-equatorial momentum and moist-static energy transports and so on. Looking at the typical vertical structure which is associated with MJO convective phase or mesoscale convective systems, so this is a conglomerate. So this is the cloudiness, temperature, and humidity associated with the multiscale tropical convective systems, which include the mesoscale convective systems, smaller scale ones, convectively coupled equatorial waves, CCEWs, eastward propagating Kelvin waves, westward propagating Rossby waves, and of course the MJO. So here is where the convection moisture feedbacks, convection radiation convection dynamics feedback, and cloud radiative feedbacks all become critical. As we said before, Kelvin waves is propagating eastward, Rossby wave is propagating westward, and the system as a whole is moving eastward with multi-scale structures where you had the 2-day waves propagating westward with a forward tilt in the front of the MJO convective system, and the eastward propagating supercloud clusters tilting backwards, and so on. So in general, you have wind anomalies, trade inversions associated with the MJO driven circulation, so subsidence ahead and behind of the main convective phase, where you have very warm moist air rising with deep convection and an extensive stratiform cloudiness behind it. So you have moist air above, dry cold air below, but here warm moist air ahead with shallow cumulus and congestus clouds and heating that is critical to create instabilities, moist static energy from advection and divergence at the top, and air-sea interactions which affect the latent heat exchange and moisture supply to the lower atmosphere into the free atmosphere, and westerly anomalies on the back side, easterly anomalies on the front side. All these great things we already talked about, right? There is the tropopause and so on. So these details are not well captured by the models. Models don't do the convection moisture feedback, convection dynamics feedbacks, and the cloud radiative feedbacks. They do eastward propagating features that are either not as strong, not propagating at the right speeds, not carrying the right amount of rain, and so on and so forth. So these have to be understood. This is an example of the moisture feedback. So if you look at column relative humidity and precipitation, there is a high relation once a threshold is crossed. So there is no precipitation when the column relative humidity is low. But once you begin to cross 0.6 or so, then relative humidity and precipitation picks up very rapidly as relative humidity increases. That tells you about the moisture convection feedback processes. And this is a nice detailed plot of time longitude evolution of precipitation in millimeter per day for 1st November to January 1st November 2018 to January 15 of 2019. Again, this is the Global Precipitation Mission data, 0.5 hourly integrated multi-satellite retrievals from GPM Global Precipitation Mission. And you can clearly see these are the longitudes, of course, and time going up. So you have clear eastward propagations that you expect from MJOs, but within that you have westward propagating 2-day structures and eastward propagating supercloud clusters. And so the clear multi-scale structures that we looked at before are all captured so nicely by this precipitation data, which is at very high time resolution and spatial resolution. Okay, so obviously models have a hard time doing this, but cloud resolving models and very high resolution explicit convection models, as opposed to convective parameterization models, tend to capture some of these features as well, at least in terms of the statistics. Okay, so the predictability of MJO then is obviously a big question. Theoretically, it has a predictability of 5 to 7 weeks, but obviously in practice this level of predictability is not accomplished by the models because of the various biases and so on, maybe initial conditions, coupled versus uncoupled models, and so on and so forth, and spatial resolution as well, in addition to the processes that we already mentioned. So we will go through the details of what the research shows, what the biases are, and what the future looks like for MJOs and process understanding, predictive understanding, predictions, and prediction skills. Okay.